Hi everybody, this is Nico from qutools. We're a very small company from southern Germany that specializes in developing and selling state-of-the-art high-performing laboratory equipment like the QTech time-taking device, for example, or the QDIS distance measurement device. But we also develop and produce educational devices for use in laboratory courses or even for high schools and for demonstrating basically quantum phenomena. This is also the topic of my talk today, which is quantum entanglement, and I'm going to show the concept of it very shortly, and then we'll start right into a demonstration with our quED Entanglement Demonstrator that I also have with me here on the side. I'm going to have some slides, but we're also going to have a look at the real device and see real measurements on a real quantum system. The phenomenon of entanglement is also known as the Einstein-Podolsky and Rosen paradox. They wrote a paper about it in 1935, where they said, look at the theory, we have found something in here that doesn't seem quite right. I'm going to start my talk by having a look at the theory and how quantum entanglement is defined in the theory. And afterwards, we're just going to have a look at the experimental setup that I have. I'm going to explain what exactly we're trying to accomplish here and what the system is doing. And afterwards, we're going to have a closer look at the results and try to interpret them and see what this all means. And then, if we still have time in the end, I will also show you a little bit of our other products, which is the Quantenkoffer and the qED, which make up our educational line together with the qED that we're going to have a look at today. In quantum theory, we describe states of quantum objects. A state contains more or less all properties of a given system, and the system can be made up of only a single particle, but it could also be made up of multiple particles. And if we have multiple particles and describe the system of this combination of particles as a quantum mechanical state, then it can happen that the state is entangled. That would mean that in the theory, in the math, in the formalism, you cannot write the state of the system as a whole as the combination of two different systems containing only a single particle and while still having all the properties. In quantum theory, a state describing the properties of multiple particles is called entangled when you cannot separate the state. That means that you cannot look at each particle on their own separately with all their properties and combine them afterwards into a single state. Instead, when you describe it as an entangled state as a whole, you can describe the measurement outcomes correctly, but if you take into account all the different particles that make up the state separately, you cannot describe all measurement outcomes. So this entangled state, the state that describes the whole system, has more properties in it than the different separate systems have on their own. From now on, we'll have a look at the easiest system, which means our system will be made up of only two particles that can be entangled or that cannot be entangled. On the left, you can see my representation of two entangled particles with all their properties. This should be a line around them. And on the right side, you would see two separate particles with all their properties around them. But this is not the same. You cannot write this entangled state on the left as a product state of these two separate states on the right. In the formalism, this would look like this, where you have also the entangled state on the left, and on the right you could try to formulate some kind of separable state, which is separated by this tensor product. And this is not possible for some states, but for other states, like in the bottom row, this is of course also possible. If you're not familiar with the formalism, just ignore the equation for the moment. We're going to have a look at what this means in the experiment in a minute. Before we do that, we should have a look at the experimental system that we use, which is our qED Entanglement Demonstrator. Basically, it consists of two parts. One part sits in this gray box over here, which is all the electronics and also the photon detectors and then there's an optical part on the right side where we produce the entangled state and where we can also measure its properties. As I've just said, we're using photons as a quantum system. 2 photons are produced in this white box, and we can choose to either entangle them or to not entangle them. The 2 photons are then coming out of this small black hole over here, being reflected on a mirror, one of them on each of these. They will pass some polarizers, and in the back they can be coupled into fibers and go towards single photon detectors that sit in the other green box, where the photons are counted, and we can detect some other stuff as well. And in the end we're going to see the measurement results on the screen, from which we can also select which kind of measurements we want to make. So let's first understand how we produce the entangled photon state. The entangled state is produced by the process of SPDC, which means spontaneous parametric down conversion. Basically, a photon from a pump laser that has a high power hits a nonlinear optical crystal, in which there's a very small probability that this one high power photon, which in our case is 405 nanometers, will be transformed into 2 photons that are down converted, which means they have 810 nanometers in our case. Just doing this does not lead to an entangled state automatically. What you have to do is you have to include some more nonlinear optical crystals and make sure that everything is aligned very, very carefully and correctly. And we do this inside the white box that I'm going to show you in a minute. And afterwards you can get your entangled state through the polarizers and into the fiber, and you can make other experiments with it. To consider this more closely, let's also have a look at our homepage, where we have an SPDC source animated and where you can insert and extract some of the optical elements. So here you can see how 1 photon of the laser is transformed into 2 down-converted photons in the BBO crystal. Those are then coupled into the optical fibers. On the bottom you can also see the polarization state of everything, which I will talk more about later. And you can also see the Dirac notation right at the bottom. So this state is not entangled. So if we now insert another BBO crystal with its optical axis rotated by 90 degrees with respect to the first one, then we have to make sure to be able to pump the second BBO crystal by inserting a half-wave plate into the pump laser, so that we change the pump polarization in a way that it now can activate both of the BBO crystals. So like this, there's a small chance in both BBO crystals that a down-converted photon pair is generated, and each of those can be coupled into the single-mode fibers in the end. But as you can see, the 2 photons do not arrive simultaneously at the optical fibers, and therefore you could, in theory, determine from which BBO crystals they originated when having a look at the detection times. In order to compensate that, we can introduce 2 IVO crystals, which are the compensation crystals. There's one pre-compensation crystal and one post-compensation crystal. And with those 2, we make sure that the photon pairs coming from the second half of the BBO crystal arrive at the same time and look exactly alike to the photon pairs originating from the other half of the BBO crystal. And if we do all that, and we do everything right, then in the end we have an entangled photon state, and we can use that to make our experiments. This is how it looks in real life then. Here is the optical pump laser at 405 nanometers. The pump beam will come out in the front, pass some lenses for beam shaping purposes. We're going to have some mirrors to align the beam correctly, an alignment target for easy alignment in the end. This is the wave plate that we can insert or remove from the beam path. The 2 pre- and post-compensation crystals, and the heart of the source, the BBO crystal, sits here. There are both BBO crystals in this one optical plate, and they are optically contacted together in order to have them as near to each other as possible. All of these source components are in this small white box over here that you can put over the source in order to minimize safety issues. So basically, with this 405 nanometer pump laser, you would have to take laser safety precautions, wear safety goggles and so on. But with the box covering the pump laser and with a long pass filter in the output of the box blocking the pump beam and letting out only the down-converted single photons, you can safely experiment with them and do not have to worry about damaging your eyes. After the single photons are coming out of the white box, we are having two mirrors that reflect the single photons. We have this inner arm and an outer arm, and in both arms the photons can pass a polarizer and are coupled into single mode fibers in the end here, where they are led to the detectors in the control unit and where we can detect single photons. This is a schematic of the control unit, the QCR, and also how everything is linked together. So here you can see the white box, the optical part. The laser in the white box is driven by a laser driver from the QCR control unit, and the down-converted photons from the fibers are optically connected to 2 to 4 APDs in the control unit. APDs are avalanche photodetectors that can detect single photons. For each single photon that is detected, an electrical pulse is generated that can be measured and counted in an FPGA inside the device. All the measurement results are transmitted to a Raspberry computer. This Raspberry computer is there for experiment control and also for display of the results. You can see here also that you can have a motorized version with a motor driver that will drive the polarizers, for example, or the motors in some additional motorized add-ons, and we can also insert USB sticks to save the measurement data for later analysis. Additionally, we have a network connection that allows connection of a VNC protocol with which you could copy the screen onto a large screen like a beamer or anything. And you also have an HTTP interface with which you can control everything also remotely. So with this standalone tabletop setup, we can now start to have a look at what entanglement actually is. We have to start with some of the polarization basics, and we're going to touch some other experiments that you can do with the device, until in the end we're going to see what polarization entanglement is, how we can describe this, and we're also going to perform a band experiment. So let's take one step back again. We now have a source of entangled photon pairs, which means that we have two photons that are coming out of the source that will travel through space, and in the end they are going to be detected on APDs. APDs are avalanche photodiodes that transform the single photons into electrical pulses, which you can see here. But how would we measure entanglement of the photons here? The photon pair that we produce is entangled in the polarization degree of freedom. The polarization is just one quantum property of a photon. Of course, there are a lot of other properties like wavelength, coherence length, and so on. But polarization is one of the easiest properties to measure and to see entanglement with. So with that, let's not delay any further and let's have a look at the experiment. As you can see, I have the qED optical part over here. The source is situated in the white box, and the single photon pairs are coming out at this hole in the front, being reflected by this mirror, passing a polarizer that I've put into a beam path already over here, and going into a single mode fiber, while the other photon of the pair is being reflected by this mirror and being coupled into this fiber. But for the beginning, we'll just have a look at the one arm over here to see how we can measure polarization and what polarization actually is. As you can see, I've also put a camera over here with which you can have a closer look at the position of the polarizer. You can see that the polarizer itself has a line over here where you can see that the polarizer is now aligned horizontally. Also, on the screen here, I have the laser already turned on, and I have it set such that I can see the count rate of this detector over here, where the photon passes the polarizer and is detected in the control unit, is counted with the blue curve. So what you can see with the blue curve is the count rate for every 100 milliseconds that I measure here. And you can see that if I put my hand in the beam path, then the count rate drops and I will not detect any more photons. And if I go out again, I can see the photons again. So what will happen when we rotate the polarizer? I have a small control in the top of the screen where I can set the angle of the polarizer with a knob on the control unit. And as you can see, while rotating the polarizer first to 45 degrees, then to about 90 degrees, and even further, there's no real change in the count rate. It changes slightly, but not by much. So what does this mean? This means that the polarization state that hits the polarizer is basically undetermined. We have unpolarized light coming in at the moment. Therefore, I will set this polarizer back to the 0 position, and we'll define the count rate that we get here as 100% of photons passing the polarizer. Additionally, I will now introduce also a second polarizer that has in the beginning the same angle than the first one, and I'll insert this directly behind the first polarizer. As we can see, since the polarizers are aligned in the same direction, the count rate does not change by much. This means that all the photons that pass the first polarizer also pass the second one. So, in another manner of speaking, when we ask a photon, "Are you horizontally polarized?" and it answers with yes for the first polarizer, then of course it will also answer yes for the second polarizer. So let's see what happens when we turn the second motor to a 90-degree angle with respect to the first one. As you can see, the count rate drops to almost 0, which means that photons that answer yes to the question if they are horizontally polarized will almost certainly answer no when they are asked if they are vertically polarized. This means that being horizontally and vertically polarized would be two properties that are exclusive. So a photon can either be horizontally or vertically polarized. So what happens when we ask yet another question? For example, are you 45 degrees diagonally polarized? And if we do that, then you can see that about 50% of the photons that we had before will answer yes to that question. So a photon answering yes to "Are you horizontally polarized?" will answer about 50% of the time yes to the question "Are you 45 degrees polarized?" Also, as you can see, when coming ever closer to the value of the first polarizer, like for example with 22.5 degrees, we get about 85% of the photons saying yes. So it's an ever increasing amount the closer the two angles of the polarizers are to one another. And this helps us to measure the polarization of a stream of photons that's hitting a polarizer. We can just turn the polarizer to different angles and see for which angle the amount of photons saying yes, so passing the polarizer, is at a maximum, and we can determine the polarization of the photons coming through. In this case, it is of course 0 degrees, since we have set the first polarizer to 0 degrees. So let us change the angle of the first polarizer that you can also see in the picture, like for example to 45 degrees. If I now go back to changing the polarization of the second filter and trying to measure the orientation of the first one, we're just trying to get to a maximum somewhere. You can see we've passed it, so we're going back a little bit. And we can see that at about 45 degrees, there's a maximum in the count rate, which is exactly the angle that we've set the first polarizer to. Correspondingly, when going to minus 45 degrees, which would be 90 degrees to plus 45 degrees, you can see that the count rate drops to almost 0. So plus 45 and minus 45 is also mutually exclusive. I've also made a slide summarizing the results of the experiment. As you can see, we have defined the amount of photons that we measure going through one polarizer as 100% of the photons coming through. And with respect to that, we have measured the amount of photons going through a second polarizer after the first one, corresponding to different angles of measurement for this polarizer. If the polarizers are oriented in the same direction, then we get almost all the photons through. If they are oriented at a 90-degree angle, we get almost no photons through. At a 45-degree angle, we get 50%, and at a 22.5-degree angle, we get about 85%. So there's only one more thing I want to show you with the single photons before we move on to the photon pairs. And basically that is when we introduce a third depolarizer. So let's go back to the experiment, where we are still in the situation that we have one polarizer at plus 45 degrees and the other one at minus 45 degrees. So they are perpendicular to each other, which means that we measure almost no photons. As you can see, there's only 1000, which is the dark count rate of our detectors. So they also make clicks sometimes when there's actually no light falling onto them. So let's go back to the experiment, where we are still in the state that one polarizer is oriented at plus 45 degrees and the other one at minus 45 degrees. So they are perpendicular, and you can see that there are almost no count rates coming through these polarizers, almost no photons compared to the 100,000 that we had in the beginning. So what I'm going to do now is that I'm going to use this handheld polarizer, that's just a polarizing foil, and put it in between those two at a horizontal angle, which is diagonal to each of those. So if I put this in between, you can see that the count rate actually rises to 25,000. So 25% of the photons that pass the first polarizer now also pass the two additional polarizers. How can this be with a polarizer being something that absorbs photons? This is a very interesting quantum phenomenon that is based on the projective nature of quantum measurements. So when you have a look at a polarizer being a projection measurement, then it also changes the state of the photons that pass through. So after the photons pass the first polarizer, they will be plus 45 degrees polarized, which means they have a 50% chance to pass through the second polarizer, which is horizontally polarized. Afterwards, they will be horizontally polarized, which means they still have a 25% probability to pass through the last polarizer, that is 45 degrees, with respect to this one, which will make up the 25% in total. You can actually also see this very well when just using 3 of these handheld polarizers. Those are cheap polarizing foils that you can get anywhere on Amazon. And you put them somewhere and you look through them, and you can see here now a lot of light coming through. And when I turn the polarizer, it's less and less and less and less light until it's almost completely dark. And then if I put polarizer in between at a 45-degree angle, you can see through them again. So as you just saw, a measurement on a quantum state can also change the state in some way. This may not seem like a big result just now, but just wait when we have a look at the photon pairs right now. When looking at the photon pairs, we have to make sure that we look at a pair that originated from the same SPDC process in the source. And in order to do that, we need some pair detection and counting device. In our case, the photons of one pair are always generated simultaneously, and the paths to the detectors are almost of the same length, which means that the photons will also be detected simultaneously. So what does simultaneous mean? In our case, simultaneous means when they arrive in a coincidence window of about 20 nanoseconds. It is very unlikely that 2 photons that come from random room light or anything will actually arrive at the detectors at this very small time window. So this will allow us to specifically look for those photons where both photons of the pair will arrive at the detectors. In the experiment, this means that we will not look at the single count rate 1 over here, but at the coincidences between 0 and 1. So the coincidences between this arm and this arm. If I put both polarizers back to the 0 position, we can actually see, I can now see a count rate of about 4,000 per second. So we see 4,000 coincidence photon pairs per second. You can now also see that this count rate will drop when I put my hand in one arm, like this, or in the other one, like this. since when in one arm no photons arrive anymore, then of course also I will not see any coincidences. So let us now have a look what happens when I remove this polarizer from the one arm and use it to measure the polarization in the other arm. Basically, when both polarizers are set to 0 degrees, we'll now get a count rate of about 35,000. Now let me turn one of the polarizers to a 90-degree angle. We see almost no counts anymore. Back to a 45-degree angle. We see about 18,000, which is exactly 50% of what we saw before. And also to 22.5, which is now almost 30,000. So about 85% of the total count that we could get with both of them at 0. This means that we could replicate the results from the single photon case also for the two photon case, with the difference that now the two polarizers are not in a single beam path, but in two different beam paths. So let's see what happens when we turn one polarizer to a 45-degree angle and use the other one to determine the maximum of the count rate and see at which angle it comes out. So if we use this motor now to try to get the best count rate, we can see that the count rate will rise to at about 45 degrees and then it will fall again, which means that 45 degrees is the angle that the photons will come in here. And if we set it to minus 45 degrees, then the count rate should drop to almost 0, as you can see here. So this is a feature of entanglement, because when we speak of this in the terms of projection measurements, then the measurement that we perform on the photon pairs on this side will change the state, just as it changed the single photon state, but this time it will change the state for both of the photons of the pair, since the system is described by a single state, quantum mechanical state. So it will change the whole state, which will also have an effect on the measurement outcome on the other photon of the pair. I have summarized all the results of the measurements also on this slide here. And as you can see, they are very much alike to the single photon case that we had before. Only that now we measure in the two different paths on two different parts of this one single two-photon quantum state. So let's have a look at one more experiment, which is called the Bell's inequality. The Bell's inequality is an experiment that is an answer to the EPR paper of Einstein, Podolsky and Rosen, where John Bell has found a way to experimentally discriminate between two scenarios. One scenario, which was believed by Einstein, is that quantum theory was not complete. He said that there has to be some kind of variable, some hidden variable, some kind of property of a quantum object that we do not take into account in the theory yet. And with this variable, all these weird results that we just saw could be explained. The other scenario is, which is what quantum theory in the standard interpretation was propagating at the time, is that what we just saw is explained because an entangled state has to be described as a whole, and it cannot be described as a separate state, which is highly non-local, since the two particles that the state is describing can be at totally different places in the universe, and still the measurement outcome that you get for one of the particles will depend on the measurement that you made on the other particle and on the outcome that you got on the other particle. So basically, when you have measured them in the same direction with the same polarization angle, then both of the particles will answer yes. And if you have measured them with a 90-degree angle towards one another, you know that one of the particles will say yes and the other one will say no. So if you know the answer that one particle gave you on one side of the universe, you will instantly know what the particle on the other side of the universe will answer to the question. And you will know this only if the questions are in the same basis, so if horizontal and vertical or diagonal, but not if you have asked one particle in the horizontal basis and the other particle in the diagonal. So if you ask one particle, are you horizontally polarized, and it answers yes, you still don't know what the particle on the other side of the universe will answer to the question, are you plus 45 degrees diagonally polarized? So coming back to the Bell's inequality, we have these different measurements that we perform with different angles of the polarizers, and we calculate some value with all of these measurement results. And basically, if you have a local realistic theory, so any theory that employs some kind of hidden variables that are local, so they only attach to one of the photons and not to the whole system, then you can get a value of a maximum of 2 for this Bell value S. But quantum theory predicts a maximum value of 2.82. And with our device, we can just perform the experiment by going into an appropriate screen like this and pressing start, which is very convenient for a presentation like this. So I can still talk to you while the measurement continues. And you can see the polarizers turning to all these different angles right now. And the count rate, the coincidence count rate, is detected in the screen. And when all the 16 measurements are done, we're going to see what we calculate for the S value, which is 2.541 in this kind. And because of the high count rate that we have, we violate the classical or the local realistic bound of 2 by about 28 standard deviations right now. Which means that in this case, Einstein was not right. Quantum theory seems to be complete, and we have to live with the fact that we have this non-local behavior in our quantum world. It is very interesting to think now how we could use this quantum entanglement as a resource for something. And it's also very interesting how quantum mechanics comes up with ways that we still do not violate special relativity. So we cannot communicate by using this entanglement with more than the speed of light. We still have to somehow classically communicate, which will be with the speed of light. We cannot use this quantum entanglement to communicate faster than that. But of course, there are a lot of other applications that do work, like for example, quantum communication, quantum computation, quantum dense coding, and just to name a few buzzwords here. So with that, I'd like to conclude the part about the entanglement and the experimental part. Additionally, let me just give you an outlook on what else we can offer. For the entanglement demonstrator that you just saw, there are at the moment 5 additional add-ons that will just expand the suite of experiments you can do. Like for example, there's a single photon interferometer, the qED Michelson interferometer MI, with which you can also do quantum eraser experiments. There's the Hong Mandel, where you can see 2 photon interference, the HBT, where you can observe the particle nature of photons, the qKD, where you can perform quantum key distribution yourself, and also the tomography add-on, where you can do quantum state tomography. Furthermore, we also developed the Quantenkoffer, which is our quantum physics in a suitcase kit. And as you can see, it employs the same photon source as the qED, but it looks completely different, which is because we wanted to have it as fascinating as possible, also from an engineering standpoint. In this photon source, you have complete control over all of the degrees of freedom, because we have it fully motorized, which is a big difference to the qED, where we have glued everything down and you cannot change anything. Also, for the Quantenkoffer, we have this modular board, plain board on top of it, where you can freely put some optical tokens, which are basically mirrors or beam splitters, and you can set up your own experiments like this. With the Quantenkoffer, you can basically cover all the experiment that you can do with the qED and its add-ons. But of course, you can also think up your own experiments and set them up with the basic optical tokens on the playing board and use the intuitive software to explain the results. And then there's the third product of the educational line, which is the quED, where you can do experiments with NV centers. An NV center is an error site in a diamond that behaves just like an atom. So you can do a lot of experiments that would concern atomic physics, for example. Like you can see the Zeeman effect, you can measure optically detected magnetic resonance, and you can use this to do magnetic field sensing and stuff like this. We have now also added the capability to pulse both the laser source, the microwave source, and the photodiode in order to allow you to precisely control the quantum state of the NV centers. And with this precise control of the timing of the microwave and the laser, you can observe Rabi oscillations, you can measure the length of pi and pi half pulses, and in the end you can really control the qubit of your NV centers and perform quantum gates and algorithms with that. And let me also point you to our website, which is qutools.com, and our YouTube channel that you can find when typing qtools into YouTube, where we have a lot of additional information about our products online. So thank you all for listening to me, and a huge thank you also to Quantum Design, who is distributing our products almost all over the world and who made it possible for me to be here today to talk to you. Thanks.